Hi everybody. In this video we're going to take a look at the difference between heat and temperature. So I'm going to start with a question. There are three objects on the bottom of the screen. I want you to see if you could rank them in order from highest temperature to lowest temperature. So most of you are probably thinking that the fire would be the hottest, the iceberg would be the coldest, and the hot coffee would be somewhere in the middle. And that would actually be correct. If we take a look at some objects, though, and we try to rank them based on how much energy they have, you might be surprised. Because in this case, the iceberg actually has more energy than the cup of hot coffee. So by the end of this video, I hope that you have a better understanding of why that is. So let's start with temperature. Okay? You all have measured temperature. You all have a temperature. We know that when we get sick, our temperature goes up, and we talked a little bit in class about why that happens. Temperature really is just a measurement of the average kinetic energy, or the amount of movement of the molecules in an object. When you take your temperature, well, the molecules in your body are moving. When you're sick, your white blood cells are moving faster because they are fighting off the bacteria or the virus that's making you sick. So the faster the molecules are moving, the higher the amount of kinetic energy they have, and therefore the higher temperature the object has. Okay, so temperature is all about how fast the molecules are moving in an object. We know that any object that's above absolute zero has molecules that are vibrating or moving. So everything above absolute zero has a temperature above zero. And you all know that we use a thermometer to measure temperature. And there are three scales that we can measure temperature in. We can use degrees Celsius, degrees Fahrenheit, or Kelvin. Notice that Kelvin does not use a degree symbol. It's just a capital K. In your reference table on page 13, you have this temperature scale that we can use to convert from Fahrenheit to Celsius to Kelvin. And on the scale, there are a few important temperatures, such as the freezing point of water, room temperature, and the boiling point of water. The first thing you need to understand to use this is that each of these scales is counting by a different numerical value. If you look at the Fahrenheit scale, if you look at each little line, they're counting by twos. When you look at the Celsius scale, and you look at each little line, you'll notice that they're not counting by twos, they're counting by ones. And on the Kelvin scale, if you look at the little lines, again, they're counting by ones. So really the big thing to be aware of is that each scale is counting by something different. Now, one of the skills that we need to master is we need to be able to convert from degrees Fahrenheit to the other scales. So we're going to do a little bit of practice. On the top of your page, you have this chart here, which has some numbers filled in. I want you to pause the video and use the temperature scale from your reference table to try to convert them. When you're done, replay the video and we'll find out how well you did. All right, so pause the video at this point and give it a shot. Okay, so here are the correct conversions. Take a look. At this point, if you're within 1 degree, you're fine. If you're off by more than 1 degree, we want to practice that to get your measurements a little bit more accurate. All right, so that's temperature. So when we look at the three objects, yeah, in a fire, because there's so much heat, the molecules are moving the fastest, so it has the highest temperature. In ice, the molecules are moving the slowest, so it would have the lowest temperature. Now let's take a look at heat. Heat is very different than temperature. First of all, heat is an actual type of energy. It's called thermal energy. That's heat. Heat can also be transferred from one object to another. Heat will always go from a hotter object, which we call the source, to a cooler object, which we call the sink, right? If you light a fireplace, the heat will move from the hot fireplace to the cooler room. You can't transfer temperature. You can't give something temperature. You can give it heat, but not temperature. Now, unlike temperature, because heat is a kind of energy, it depends on two things. It depends first on the mass of the object, depends on how big it is, and it depends on the temperature of the object. So it's not as simple as just looking at whether something's hot or cold. We also have to look at how much mass it has. And then the final thing is that there are two units that we can use to measure heat. In the reference table, they use joules, which is capital J is the symbol. When we're looking at heat energy that we get from food, we measure it, of course, in calories. So when you look at a label of food, it tells you how many calories you're getting. Calories measures how much heat energy your body will get when you eat that food. Okay? So now let's go back to this idea of heat being based on the temperature and the mass. Because earlier we looked at these two pictures, and most of you were probably surprised when I said that this iceberg has a lot more energy than this hot cup of coffee. Okay? Now, clearly, the coffee is hotter. It has a higher temperature. But remember that heat is not only about the temperature, it's also about the mass. There is much less coffee in this cup than there is in this iceberg. Okay? So if we think about what energy is the ability to do work. Let's say you wanted to make something warmer or colder by using these objects. If you poured this coffee on something, you would heat up the object a little bit. If you took all of this ice and you put it on something, you would be able to make many more objects colder than what you'd be able to heat with this coffee. So because this iceberg has a much larger mass, it has a lot more energy. Okay, there's a lot more cold molecules. You could think about it like today's snowstorm. It's obviously very cold out today, but the storm has a huge amount of energy, which is why we're all home today. Now, there's one more aspect of heat that is important for us to understand, and it's something called the specific heat. If you want to heat an object up, you need to give it a specific amount of energy. The specific heat is the amount of energy that's required to take 1 gram of a material and make it 1 degree Celsius warmer. In your reference table on page 1 is a chart that shows you the specific heats of common materials. This tells you how many joules of energy are needed to raise 1 gram of the material 1 degree Celsius warmer. Okay, so when we look at the chart, we notice that liquid water has the highest specific heat. Liquid water needs 4.18 joules of energy to make 1 gram of water go up by 1 degree Celsius. That's a lot of energy. That's why water takes so long to heat up. If you look at the bottom of the chart, you'll see lead. Lead only needs 1/1300ths of a joule of energy to make 1 gram of lead go up 1 degree Celsius. So lead has the lowest specific heat. In other words, it takes a lot less energy to heat up lead. This would explain why certain things get hotter or cooler when you're outside on a hot sunny day. Okay? So let's say you are at this person's house and we're looking at 3 materials. We're looking at stone tile, water, and air. Which would be the hottest on a hot July day? Well, you probably know from experience that, let's say it's 85 degrees outside. The air is going to feel hot. The water will not be that warm. You've probably walked barefoot on stone tile, and you probably know that it often will hurt your feet. The reason the stone tile gets the hottest is because the stone tile, let's say it's made out of granite. It has a fairly low specific heat. It only takes 79 hundredths of a joule of energy to heat that up. The air, on the other hand, needs 1 whole joule of energy, and the water needs over 4 joules of energy. So that explains why certain things are hotter on a hot summer day. Now, if something has a low specific heat, it's really good at absorbing energy because it doesn't need very much of it to heat up. If a material has a high specific heat, it is a poor absorber. Okay, water takes a really long time to heat up because it requires so much energy to heat up. Now remember from class that if something is a good absorber, it's a good radiator. Lead is a good absorber. It heats up really quickly. It also cools down very quickly. Water, on the other hand, specifically liquid water, takes a really long time to heat up. That's why in the summer, if you go to the ocean, the water is never very warm. But because it takes a long time to heat up, it also takes a very long time to cool down. Water will still be warm in October. If you go to the beach in October, the water may actually be warmer than the air. That has a huge impact on climate. People that live near large bodies of water tend to have cooler summers because the water stays cooler. They also tend to have warmer winters because the water stays warmer. We're going to learn a lot more about that when we study climate. But I want to leave you with one last picture. I took this picture last year when I was hiking in Westchester, and it was sometime in March. You can see that there's no snow or ice anywhere on the rocks, on the trees, on the ground. All of those things have warmed up. When you look at these two ponds, though, you still see they're filled with ice. And the reason for that is because water has the highest specific heat. It takes a long time for water to heat up, and it takes a long time for water to cool down. All right, so we will review this in class, but this is at least gives you an introduction as to the differences between heat and temperature. See you tomorrow.